All right, ladies and gentlemen, in this one we're going to talk about the rate law. All right, so we want to know, right, the rate law is the relationship between the reactant concentration and the rate of the reaction. Okay, so that means you're going to have a rate. How fast is this going? And you're going to have a concentration. So let's give you an example, right, of a reaction. H2O2, all right, decomposing to H2O and O2 gas, right? Of course, that's not balanced, so we need a 2 and a 2, all right? Okay, the rate constant, so the rate at which hydrogen peroxide is decomposing. So if you have hydrogen peroxide at home, it is decomposing slowly, okay? That's just what happens with it. So, and we want to compare this to the concentration of H2O2. And I want to know how it compares. Right? We want to know how it compares. And so there's going to be equal there. Well, what we throw in is K. Right? And K is the rate constant. And we'll show you how K comes from in the example we're going to do. Rate constant K, it varies with temperature. All right. And it typically increases with increasing temperature. All right. Now, there's also here X. All right. X is the order of the reaction. Okay? And this is only determined by experiment. I mean, it's not the coefficient. It could be. It could be squared, but typically it's not always that way, right? You can it could be, right? You have to do an experiment. You can't just look at it, right? Now, again, the brackets mean concentration. Right? Which will be molarity. All right, so that's a rate law. So we have a concentration, right? Because the laws predict behavior. Concentration, I want to know how fast it is. So if I know I have 5 molar hydrogen peroxide, I should know how fast it's going at that temperature, right? If I know the rate law and the rate constant, okay? So if this reaction was 1, let's just say we have a first order reaction, right? We call it first order, right? That would be the rate is equal to the rate constant K times concentration at H2O2 hydrogen peroxide to the first power. It's a first order reaction, right? And the order with respect to hydrogen peroxide is 1, all right? First order. So what orders will we be talking about? Well, we would have obviously first order, And so generically speaking, first order reaction, rate equals K times concentration A to the first order. We would have second order, where rate equals K times concentration A squared. And then there's also zero order, where our rate equals K, rate constant K times concentration A to the 0 power, which is the same thing as basically rate equals K. All right. So this is a rate law. All it's doing is protecting. I'm going to show you how in a second, but first, let's do a quick example of the rate law. So if I have rate equals your rate constant K times the concentration of A to, let's do the second power, and concentration of B to the first power. All right, so let's say I have that rate law. We are second order with respect to A, reactant A. We are first order with respect to reactant B, and we are third order overall. All right, so that's the rate law. So let's dive into an example and how this is determined, and hopefully this will then tie it together with the method of initial rates. So this is how we determine the rate law. Okay? This is how we determine the rate law. Okay? Now, we have 3 experiments, and when you do the scientific method, you got to do this. And that's changing one variable at a time. So the reaction with nitric oxide with hydrogen. All right? And so we have NO plus H2, right? Okay. 3 experiments were done, different initial concentrations. What's the rate law? And what's the value of K? So we have those two. Our rate law is going to be rate equals K, concentration at NO, and concentration at H2. And some books, X, Y, MN, PZ, whatever, smiley face and star, I don't care what you use, right? It doesn't matter. But they're different, so they can't be the same thing. But we're going to try to figure out this. Now, we got 3 experiments. The first experiment, right? The second experiment, and the third experiment. So we have 3 experiments. Alrighty. And so we're going to compare them to each other. It doesn't matter what the order or whatnot. So I have my rate. Again, rate equals K. Concentration of NO to the X. Concentration of H2 to the Y. So I'm going to compare 1 and 2 and see how they compare each other. So if I look at experiment 1 and 2, what happens here? NO stays the same. It doesn't change. H2 changes. So any change in this rate is due to H2 and not due to NO. All right. And so let's look at this. Experiment, I'll do 2 first. So we'll do experiment 2. We'll just put that in. The rate is 5 times 10 to the negative fifth. And that's going to equal K, whatever K is, rate constant K, times concentration of NO, which happens to be 5.0 times 10 to the negative fourth. All right. Multiplied by the concentration of H2, which is 1.0 times 10 to the negative 3. Now if we look at experiment 1, I have 5.0 times 10 to the negative 4. I still have K. I have, for NO, I'm sorry, I messed up. I looked at the wrong thing. The rate is 2.5 times 10 to the negative fifth. K is K. NO is 5.0 times 10 to the negative 4. And H2 is 5.0 times 10 to the negative 4. So now we're just comparing these. And we got X here. And we have Y. All right. So now, if we do some math, this looks like it's what? 2 equals 1 times 1 to the X times, that looks like it's 2 to the Y. I think that's what it looks like. All right, if I simplify that, 2 equals 1 times 1 to the X, well, 1 to any power is 1, so it equals 2 to the Y power. Now, you probably don't need a calculator to solve this to know that Y then is 1. But let's review logs. So I'm going to scroll up and let's talk about logs. All right. When you have B to the X power equaling Y, right? That means the log of B, right, of Y equals X. Yay! So what does that mean in our calculator? Right? If we type in the log of Y divided by the log of B, that equals X. All right, mathematically how that works. All right. Because we're going to be solving for X in this. So that's how we can do this with logs. Now, you may remember that, and you may not remember that. It's okay if we do, it's okay if you don't, but that's how we do it. All right. So if we'd have done the log of 2 divided by the log of 2, we'd have got 1. All right. So that means we now know Y is 1. Now I'm going to do experiments 3 and 2. Why would I do 3 and 2? Well, if I look at this changes, which is good. There's a change there. That does not change. So any difference of rate here is due to NO and not H2. Now, the reason I did experiment 1 on the bottom and 2 on top is because this number is bigger than that number, if that makes sense, right? Experiment 2 has bigger values than experiment 1. You didn't have to do it that way. And now that we know how to do this in our calculator, we don't have to. But if I look at 2 and 3, right? 3 is a bigger number than 2. 3 is a bigger number than 2. So I'm going to use experiment 3 on top. All right. And so we're going to do it the exact same way we just did the first two. So let's go experiment 3. All right, my rate is 2 times 10 to the negative 4. K is K. Our concentration of NO is 1 times 10 to the negative third. Our concentration of hydrogen is also 1.0 times 10 to the negative third. And then in blue for reaction 2, our rate is 5.0 times 10 to the negative fifth. K, I have 5.0 times 10 to the negative 4 molar, and I have 1.0 times 10 to the negative 3 molar. All right. Now we know that H2's coefficient is 1, so we can use that. So if we do the math here, this looks like we get 4 equals 1 times, that would also be what? That would just be 2 to the x power times 1 to the first. So that means 4 equals 2 to the x power, so x is 2. So that means the rate law would equal K times concentration of NO squared times concentration of H2. So there is the first part of the answer. All right? And if you want to write a 1 here, just to be careful, you can. That's okay. Now, there's a next part. And that next part asked, what's the value of K? All right? It doesn't matter which one you pick. Ideally, you would do an average of K of all 3 experiments, right? Now, if we were actually doing the method of initial rates in a real science lab, right, you would do way more than 3 experiments, and you would average the K, right? And you do it on different days and all that fun stuff. But for our chemistry land example here, we're just going to do 3 experiments. I'm going to pick the easiest one, and that's going to be experiment 3. But it doesn't matter. So if I pick experiment 3, right, the rate in experiment 3 was 2.0 times 10 to, I don't know why that keeps popping up, guys, I'm sorry, times 10 to the, negative 4 molarity per second equals K, which we're looking for, times the concentration of NO, which is 1.0 times 10 to the negative 3, and that is squared, times concentration of H2, which is 1.0 times 10 to the negative 3. All right, if we do the math, all right, okay, now we also got to make sure, I'm going to put them in a different color, molarity here and molarity. That's important because K has units. And K's units are whatever we need to make it work because it's a constant. That's what constants are doing. It's just relating the concentration to the rate law. So it has whatever units we need it to have. And so that becomes 3, 6, 9, negative 9. So it looks like it's what? 2 times 10 to the 5th. 2.0 times 10 to the 5th. Now units, right? I got to have K so it cancels out and gets just molarity per second. So whatever, I have molarity squared now, so that means I have to have a molarity down here in a second. I believe that's all I need, right? Molarity, no, I have molarity cubed, so I need a molarity squared. So it's 1 over molarity squared times seconds. So if I have molarity squared, well, I didn't want to erase. I want that to be a 2. If I have 1 over molarity squared times seconds times molarity cubed, I get molarity per second. So that's what K is. So that's the method of initial rates, all right, and the rate law, right? And what we're going to do with the rate law coming up is be able to predict concentration with time, All right, and so we'll see that in the next video. If you have any questions, let me know. Otherwise, take care.